Hello, my math-hungry friends. Um, Lesson 4 of optimization and curve sketching. This is like a schwack of a bunch of different information, okay? None of it is exceptionally hard. We need to deal with odd even functions, and that's only going to take a couple of minutes. Then we want to review asymptotes. Now, review asymptotes and talk about a new type of asymptote that we haven't talked about before. We are comfortable with vertical asymptotes and we're comfortable with horizontal asymptotes, so we're just going to quickly review those. And then we're going to spend some time talking about slanted or oblique asymptotes. That's going to be a little new to us, but everything we do around trying to figure that out actually I think is going to feel super familiar to you. So I'm fairly confident that you're going to walk through this lesson and say, oh, okay, maybe I never thought about it like that, but I can do this. I got this. Like, I don't think this is going to be super, super hard on you. Okay, so here we go. First of all, we're going to talk about even and odd functions. So an even function is if f of x equals f of negative x. So essentially, even functions, are symmetric with respect to the y-axis. Okay, so if they are a horizontal reflection, or I guess I shouldn't say that it's reflected, but I guess a better way to have said that was if I was to reflect this, it would still look the exact same. Okay, so they're symmetric. So if I want to test to see if something's even, if a function's even, all I do is I replace all my x's with negative x and see what I get. If I end up getting the same function, then it's even. Now, you may be like, well, how would that ever work? Well, think about it. If I gave you y equals x squared minus 4, okay, and we replaced x with negative x, we'd be looking at y equals negative x squared minus 4. But negative x squared is still just x squared. So this guy is an even function. This guy would be symmetrical about the y-axis, okay? And you know that if you think about the drawing of that, right? That's just a parabola that has a vertex down at negative 4, right? So we can see that it's symmetrical about the y-axis. Okay, so that's an even function. If you want to test for an even function, you replace x with negative x, and then see if you get out the same thing. Okay, an odd function, f of negative x equals negative f of x. Okay, so if f of negative x equals negative f of x, then the function is odd. And I've shown you an odd picture there. I'm just going to hide myself for a quick sec in case my big old head is in the way. Okay, there is an odd function. Odd functions are symmetric with respect to the origin. So essentially, they look the same as if they were reflected in both the x and y axis. If I took this fella right here, okay, and I reflected that in the y-axis first, I would end up with something that looks like that. And then if I reflected it in the x-axis, I would end up looking like that, okay? So that's what we mean by they're symmetric with respect to the origin, okay? Okay, now to test for an odd function, well, first you test for an even function, right? Because an even function, you just replace all your x's with negative x. The odd function says, hey, f of negative x is going to be the same as negative f of x. So by testing for an even function, you have already figured out what f of negative x is, okay? Now you're going to see what negative f of x is and see if those guys are the same. If those guys are the same, then you can determine that your function is odd, okay? Okay, so classify the following functions. Y equals x to the 8. Well, first we're going to check for an even function. So we're going to find f of negative x. If that doesn't work, you're already halfway there to checking for an odd function, okay? So I'm going to replace x with negative x. And if I do that, negative x to the 8 is still x to the 8. So f of negative x is the same as f of x. So my function's even, okay? Okay, y equals x cubed plus 1 over x. So the first thing I'm going to do is test f of negative x. Okay, so that's going to give me negative x cubed minus 1 over x. So f of negative x is not the same as f of x. This is not an even function. Okay, so now I'm going to say, okay, it's not even. I'm already halfway to checking to see if it's odd. So now to see if it's odd, I'm going to figure out negative f of x. Well, negative f of x would be that right there. Well, that would give me negative x cubed minus 1 over x, which is the exact same as f of negative x. Okay, and so the function's odd, just like my mama told me I was. So negative f of x is negative bracket x cubed plus 1 over x. The function is odd. F of negative x is the same as negative f of x. Okay, I know when you just listen to me, that sounds confusing. Okay, it's not. You just have to think about it for a second. Okay, if x gets replaced with negative x and I get the same thing, I'm even. If I'm not even, I test to be odd. And the way I test that is I put a negative on the whole equation. So if negative, the whole equation, equals the same as that f of negative x that you previously just solved for, then you know you have odd. If it's not even and it's not odd, it's neither. Okay? All right. Good. That was it for our even and odd talk. See, I told you that was going to be relatively quick. Let me just get the ink off there. Okay, so given f of x equals 1 over x squared, determine the limit of f of x as x approaches 0. Well, you can see based just on the visual, the limit doesn't exist, but it approaches positive infinity. Okay, clearly f of x is undefined, does not exist at x equals 0. So what we want to do is we want to test, just like we did with limits, we want to test close to the left and close to the right. Okay, so I've given you a couple of numbers to try. I'd like you to plug these numbers in your calculator and get values out for me. You can pause me and do that. Welcome back. Here are the numbers that you should have gotten. Okay, and we can clearly see right now that those y values are increasing. We say y increases without bounds, okay? They're just getting bigger and bigger and bigger and bigger. Okay, so from this we can conclude that the limit of f of x as x approaches 0 is infinity. Now, again, remember my little lecture all through our limits. The limit doesn't exist, but the graph heads to positive infinity, okay? And all of those things you should be very, very comfortable with at the moment. Like nothing in this part is really all that new. So the function f of x will have a vertical asymptote at the line x equals a if we have any of the following limits. So if the limit on the left approaches positive or negative infinity, if the limit on the right approaches positive or negative infinity, or if the limit in general on both the right and left approach positive and negative infinity, okay? Either one of those creates a vertical asymptote, okay? So like for instance, I'm just wondering if you might have trouble visualizing what I just said. So like, here's an example. Okay, there's a vertical asymptote right here. So we can say the limit on the right is approaching negative infinity. There is no limit on the left. That doesn't mean there's not a vertical asymptote, okay? So it could be on one side or it could be on both sides. Totally cool, okay? Okay, oh, I don't know what happened there, sorry. Okay, now, to find vertical asymptotes, determine which values of x make the denominator equal to 0. And then find the one-sided limit at these points. So for some practice, determine the vertical asymptotes for the following. So we have f of x is 2 minus 5 over x minus 6 all squared. 6 is going to be our point that we're thinking about because that's going to make the denominator 0. So I'm testing 6 on the left and I'm testing the limit for 6 on the right. The limit for 6 on the left, again, to test that, you're just putting in your calculator something that's close to 6 from the left. So like 5.9, 5.99, 5.999, and see what happens. And it's going down to negative infinity. Okay. Likewise, 6 on the right is also going down to negative infinity. Okay, so 6 on the right would be like 6.1, 6.01, 6.0001. I'm approaching it from the right. Okay. All right, so there is a vertical asymptote at x equals 6. Okay. Okay, try this guy then, determine the vertical asymptote. We probably want to factor that first, right? Looking for two numbers that multiply together to give me -6 and add together to give me -1. That would be -3 and 2. And so I have to check x equals -2 and x equals 3, because those are the spots that would make the denominator 0. Okay, so I'm going to check -2 on the left and on the right. I'm going to check 3 on the left and on the right. You're going to do that first. And you've got 3 on the left should have been approaching negative infinity, and 3 on the right should have been approaching positive infinity. And then -2 on the left should have been approaching negative infinity, and -2 on the right should have been approaching positive infinity. Okay. So for sure, that fits the definition of a vertical asymptote. At least one side is approaching infinity. On these ones, both sides are approaching infinity. They just happen to be in opposite directions. So we can say that there's a vertical asymptote at x equals 3 and at x equals 2. Sorry, x equals -2. Okay. Okay. Now, just as you're following along in your book, there's a practice time now just for vertical asymptotes and even and odd functions. I'm going to keep going, so I want to talk about horizontal asymptotes and slanted asymptotes next. So I'm just saying at the moment, you're going to just flip over a couple of pages to where it says horizontal asymptote. Just don't forget to come back and do that practice time, okay? Okay, so now we're going to talk about horizontal asymptotes. Sketch the graph of f of x equals 1 over 4x plus 3 and determine the limit as x approaches infinity. Okay, so what's occurring as x approaches infinity? Well, if we took a look at that graph, it would look something like this. Okay, and we can see that it looks like as x approaches infinity, y is approaching 0. Okay, it looks like that x-axis seems to be a horizontal asymptote. So y approaches 0. Okay, now how could we determine this without a picture of the graph? Well, here's why I said this should sound familiar. We already did this, right? When we did sequences in series, when we did the sum of a geometric series to infinity, we talked about finding horizontal asymptotes. And what we did was we divided by the largest power that we saw in the denominator. Okay, so I had 4x plus 3, so the largest power I saw in the denominator was just x to the 1. So I divide all my terms by x to the 1, and then that's going to give me, I just simplified this, so the 4x over x gives me the 4. This ends up becoming 0, and this ends up becoming 0. Okay, and so 0 divided by anything is 0. Okay, so algebraically, that's how we figured out horizontal asymptotes. So you already know this part, right? This is nothing new to you. Okay, so let's do it again. We're going to take this guy and we're going to solve graphically first. So grab your graphing calculators if you haven't already done so. And we're going to try and figure out what's happening as x approaches infinity. Well, when I look at this graph, as x approaches infinity, it's approaching somewhere along here. Just let me throw a line in here for a second. It'd be somewhere along here. Okay, but I'm not quite sure what that is. And my line that I just drew there is probably a little wee bit too high. Okay, but it looks like it's approaching 1/3. Now, some of you are going to say 1/3 anyway, because either you remember what to do here and you've already just shut me up and divided everything by x squared, or you have gone back to your 30-1 days and you said, hey, this is the same degree over the same degree. It's the leading coefficient over leading coefficient, 1 divided by 3. Right? You've got lots of tools in your toolkit here on how to figure out where that asymptote is. But the algebraic calculus way we will do it is to divide all of my terms by x squared, because x squared is the highest power that I see in the denominator. Okay, so let's go ahead and do that. We're dividing everything by x squared. Okay, here that's going to get me 1. This is going to be 0. This is going to be 3. This is going to be 0. This is going to be 0. And that's where I get the 1 over 3. Okay. Awesome. Okay, so for horizontal asymptotes, if direct substitution yields infinity over infinity, then it is useful to divide the numerator and denominator by the highest power of x in the denominator, then simplify and then attempt direct substitution. Okay, so that's how we're algebraically solving for the horizontal asymptote. Okay, so recall horizontal asymptotes, the value of the function as x approaches x, the value of function approaches as x becomes larger in the positive or negative direction. Okay, so another way of looking at that is we could say the limit as x approaches positive or negative infinity, 1 over x to the r, where r is greater than 0. The other way to look at it would be 1 over a really, really big number. Okay, if you think of just what happens if I put 1 billion in for x right now, what's happening to this overall function? Okay. So whenever we have 1 over x to the r, where r is greater than 0, we end up being 0. Okay. Okay. The function f of x will have a horizontal asymptote at the line y equals L if either of the following are true. Either the limit to as x approaches negative infinity is L, or the limit as x approaches positive infinity is L. Okay, I don't need it to go for both directions of infinity. Okay, I only need it to go in one direction of infinity to call it a horizontal asymptote. Okay, so these are all examples of horizontal asymptotes, okay? Just to try and bring that point home to you, like if you look at this first guy here, the horizontal asymptote isn't true over here at all, but it's true over here, okay? Same thing here, same thing here. It's not true at all here, but as x approaches infinity, it levels off to that asymptote, okay? So these are all just different examples of how you can get a horizontal asymptote as x either approaches positive infinity or approaches negative infinity, or both, okay? Okay, cool. So to find horizontal asymptotes, we're taking the limit of y equals f of x as x approaches infinity and as x approaches negative infinity. Okay, so things to remember. This first one we already just talked about. If it's 1 over x to the r and r is greater than 0, that limit will always be 0. Number 2, we divide every term in the function by the highest power of x in the denominator. And then 3, if the limit is infinity, that means there is no limit and there is no horizontal asymptote, okay? So if as x approaches infinity, y approaches infinity, that's not an asymptote, okay? Or as x approaches infinity, y approaches negative infinity, it's not an asymptote. Y has to be approaching a particular number in order for it to become an asymptote, okay? So the limit actually has to exist. Okay, so determine the horizontal asymptotes for the following. Okay, again, we're going to do this from a calculus perspective. We're dividing everything by x squared because that's the highest power on x in my denominator. And that's going to simplify to 3 over 5. Okay? Yes, you have to show that to me. I know some of you are sitting there saying, do I have to show you that? Yes, you have to show it to me. It's about your calculus communication. Okay? Okay, so let's try this guy. We're going to divide everything by x squared this time, because that's the highest thing I see in my denominator. This guy up here is going to simplify to 1 over x, which ends up being 0 over 1 minus 0 minus 0. Okay, so 0 over anything becomes 0. So that would be 0. Okay. All right, and then this guy. I'm waiting for you to think about some things. This is a polynomial function. There is no horizontal asymptotes in a polynomial function. Okay. think about it for a sec. If you don't like the fact that I'm just saying none, some of you might be scowling at me at home. Think about it for a sec. Just put a really big number in for x. Is everything kind of converging in one point? No, it just keeps growing or keeps shrinking or whatever it's doing. Okay. Okay, so now we are going to turn our attention to a new type of asymptote that we haven't really talked about before. Oblique or slant asymptotes. Now, just to kind of give you the take-home message before we start, you get graphs that look like maybe something like this. And we've seen graphs that look something like this before, okay? But what I want you to notice, what I want you to keep in mind is really, there's an asymptote right there, that this guy here is riding towards this way, and this guy here would be riding towards this way, okay? So in the example I've drawn you here, there's this slant asymptote, and then there's probably this vertical asymptote here, okay? So what we want to try and do is we want to try and figure out how to find the slanted asymptote, if one exists, okay? And actually, how to find one becomes really easy. I'm just going to kind of walk you through a quick investigation to show you what we're talking about, but it comes from something you've already done, okay? So that's where we're going. Now we're going to back up, and I just kind of want you to go step by step with me for a sec. So consider the function y is 4x squared minus 4x minus 3 all over x plus 3. Let's use long division to determine the quotient and the remainder. We've done this in several settings already, between 30-1 and already in calculus as well, okay? So if I want to divide that polynomial by x plus 3 goes on the outside, 4x squared minus 4x minus 3 goes on the inside. I need to make sure every degree is represented, and I need to make sure that I'm going in the right order of descending degrees. So now I'm asking myself, what do I need to put up here so that when I multiply it by x plus 3, I will get that 4x squared, so I can get rid of the 4x squared. Well, I need a 4x, so I put the 4x on top. 4x times x is 4x squared. 4x times 3 is 12x, and now I'm ready to subtract. So 4x minus 4x is nothing. Negative 4x squared minus 4x squared is nothing. Negative 4x minus 12x, that would give me negative 16x. So now I'm looking at negative 16x minus 3. What do I need to put up here so that I get rid of the negative 16x? Well, I need to put a negative 16 up there. So I go ahead and do that. And then I do the subtraction, negative, oh, that should have an x right there. Let me just add that in for you. X, okay. So then negative 16x minus negative 16x is nothing. And then I get negative 3 minus negative 48 will give me a remainder of 45. Okay. Now, there are essentially 4 different pieces to this question. We have q of x, r of x, n of x, and d of x. Now, we've done this once or twice before. Take a breath. I'm going to go through each one, okay? Q of x is the quotient polynomial. Well, that is what my answer is, okay? That is what happens when I divide. R of x refers to the remainder polynomial. N of x is the original numerator, and d of x is the original denominator, okay? Okay, great. So I can actually write this, I'll clear that ink for you. I can actually write this original polynomial, 4x squared minus 4x minus 3 all over x plus 3. I could write it as 4x minus 16 plus 45 over x plus 3. Okay? Okay. So here's where we start a little investigation. Let's compare the y values of my original function, my y1, with the quotient, which was just that 4x minus 16, right? The plus 45 over x plus 3 was the remainder. A reminder, it's over x plus 3 because that's the part that never actually got divided by x plus 3. So we still have to divide by x plus 3. That's where that fraction is coming from, right? Okay, so we want to compare this guy to this guy for a second, okay, as x approaches positive or negative infinity. So what I'm going to do is we're going to set up some tables, and we're going to have one table approach positive infinity, and we're going to have another table approach negative infinity. Okay, so here we are going to do positive infinity first. Now this is going to take a minute. You got to do some button pushing. Plug in negative 10, negative 20, negative 30, negative 40, negative 50, negative 100, and negative 1,000. I want you to plug that in for both the y1 and for the q of x. Okay, remember the q of x is 4x minus 16. So pause me and do that. Okay, and then these would have been your numbers. Now, here's what I want you to notice. Here's what I'm really hoping you'll notice. As x gets bigger or gets more negative, sorry, I am trying to change the color of my ink while I'm talking to you, and I'm doing a horrible, horrible job of it. Okay, so as x approaches a larger negative number, what I want you to see is the y values become the same thing. Okay, they weren't the same thing at the beginning, but they actually become closer and closer and closer to each other as we get to much farther away values for x. Okay, so the output of y1 and q of x become the same thing. Well, that's interesting. Okay, let's go to positive infinity instead of negative infinity. Okay, so now I've got 10, 20, 30, 40, 50, 100, 1,000. I'm going to give you a second. Well, actually, no, you're going to give yourself as much time as you need because you're going to shut me up for a sec. Do this and then come back. Okay, so we end up seeing the same thing, okay? At first, at 10, they're kind of far apart, but as we keep getting bigger, they look at 30, they're 105 versus 104. At 40, they're 145 versus 144. And then by the time we get to 1,000, they're 3984.0 something something and 3984. So they're pretty darn close together. They're pretty close to touching each other. Okay. So the aha moment that I want you to have is this function is approaching this guy. Now, why would that function approach that guy? Because there's still this other piece here. But think about this for a second. As x gets super big, what can you tell me about this fraction? As x gets super big, that's just going to approach 0, right? 45 over a billion is just pretty much 0. So as x approaches positive or negative infinity, that remainder fraction becomes obsolete, and we're just left with the 4x minus 16. And so the 4x minus 16 is the equation of our slanted asymptote. Okay, so what can we say about the values in y1 relative to the values of q of x as x approaches positive and negative infinity? Well, we can say the values approach, oh, sorry, I'm having technical difficulties here. Again, these are technical difficulties that you can't see, but I had a control panel in the way of my wording. The values of y1 approach the values in q of x, okay? Okay, so consider the graph of the two functions. So my blue graph is my original y1, and my red graph is that q of x, okay? So as x approaches positive or negative infinity, the graph of y1, that 4x squared minus 4x minus 3 over x plus 3, approaches the line 4x minus 16. So it's that line that we're going to call the oblique or the slant asymptote, okay? And to get it, all we have to do is we end up doing the long division of the rational function that we see, okay? So in that sense, that part's familiar because we've practiced long division of a polynomial before. So an oblique asymptote is a non-horizontal line which the graph of a rational function will approach as x approaches positive or negative infinity. Okay. So knowing that y1 equals 4x squared minus 4x minus 3 all over x plus 3 can be expressed as y2 equals 4x minus 16 plus 45 over x plus 3. Knowing that both of them can be expressed, are expressing the same thing, why does the graph of y1 approach the graph of just q of x as x approaches positive or negative infinity? I've already answered that question. It's because as x gets really big, this fraction that I'm circling with my mouse right now just becomes obsolete. Okay, consider the limit as x approaches plus or minus infinity for 45 over x plus 3 gets closer and closer to, or sorry, of y2. The fraction gets closer and closer to 0 as x approaches infinity. So the graphs of y1 and y equals 4x minus 16 are going to get closer and closer together. Okay. You've explained why the graphs are close to each other as x approaches plus or minus infinity. Give one possible reason why they are not close to each other near x equals negative 3. Well, really, it's because that remainder fraction is having more of an effect, okay? So when x is near 3, the value of 45 over x plus 3 is relatively large, so it's not close to 0, which means it's having an effect on the graph. Therefore, the graphs will not be close to each other. For example, substitute x equals negative 2.5 into the rational function and the quotient function, okay? So what we're saying is, when the numbers are smaller, that fraction remainder has more of an effect, and that's why they don't meet each other. As the x values get larger, that fraction remainder has no effect or nil effect, and therefore the quotient function and the original function are much, much closer to each other. Okay, so you were asked to substitute x equals negative 2.5. If I did that into y1, I'd get out 64, but if I did that into q, I'd get out negative 26. So they're fairly far apart from each other. Okay, and that's because my x values are small right now. So in summary, to determine the equation of an oblique asymptote, use long division to determine the quotient polynomial. This is the equation of your oblique asymptote. An oblique asymptote may exist for a rational function when the degree of the numerator is greater than the degree of the denominator. So that's when you want to check that, okay? When the numerator has a higher degree than the denominator, you want to do that division and look for a oblique or slant asymptote, okay? It's also worth noting that oblique asymptotes don't have to be linear in nature. The one we did in this example, and even the one I just drew up here, was a linear one. But in fact, oblique asymptotes may have other degrees, okay? If we were to take a look at this graph, and I showed you both of those polynomials again, what we see is as we approach infinity on both sides here, the blue and the red are going to get closer and closer and closer to each other. Okay. Awesome. Okay, so that's it for this lesson. Your homework is there. As always, I'm only an email away. Make sure you connect with me if you do have any questions as you're going through it. And then next up for us will be a talk on the second derivative test and concavity. That'll be super fun. Okay, so I will see you there. In the meantime, have fun. Take care, guys.